It's an eye-glazingly boring topic today, but a necessary one, and something that you've already seen in the lab practicals in the first years. That is the propagation of errors in uncertainties through your calculations. We have by now gone through all the necessary prerequisites, that is, you know, all the things, derive these expressions, and what we'll do today is actually do it, derive, discuss, and take a good look at the applications of them. And I will also show you a few scenarios where inaccuracies and uncertainties behave in unexpected ways. So you can occasionally take some wildly inaccurate quantity and obtain a rather accurate result from the calculations, which would be fortuitous, but unfortunately it's rather rare. What normally happens is, as you are doing calculations, uncertainties proliferate, sometimes to the extent that the end result of your calculation actually becomes useless. So before I begin with all the boring mathematics, let me give you a few examples of that. Imagine you are calculating something like the pH from concentration. So if that's your concentration of your hydrogen plus ions, and that's your pH, let's say minus pH for convenience, then you know it's a logarithmic function. So it would be something that would look roughly like this. Logarithm is a fairly slow function. Imagine now that you are measuring the concentration of your protons with, well, quite some inaccuracy. So your concentration measurement device would be rather uncertain, and so your standard deviation on the hydrogen concentration, so CH plus, would be large. So perhaps even as large as 50%. You would discover, however, once you've computed the logarithm, that a huge uncertainty in this parameter would in practice translate to a tiny uncertainty in the pH. That's the example of a fortuitous situation where something rather inaccurate that goes into the calculation produces the result with a rather decent standard deviation relative to the amplitude that there is. There are, of course, opposite situations where if you are doing the calculation that is instead restoring the concentration of the hydrogen plus ions from your pH, so let's say that's your minus pH, then of course you know that that is an exponential function and it will grow rather steeply. Something like that. In which case a tiny uncertainty in the pH, let's say something like that, that's your sigma pH, would translate to a very considerable uncertainty in the final answer. So this function dampens inaccuracies. This function amplifies them. And of course, the reality in any practical calculation would be some combination of the two. You would have some variables to which your function is rather sensitive, and you would have others to which it is not sensitive, and you'd better know which those are. And the subject of today's lecture is exactly that. Now, the bad news, unfortunately, is there is in general no recipe for propagating uncertainties through a nonlinear function. However, as you can probably see in both cases, a local linear approximation to this is actually pretty good. So, we draw the tangent line here and the tangent line there. If we were to use, instead of the function itself, the tangent line as a way of propagating these uncertainties, you can see we wouldn't get it terribly wrong. And so the topic of today's lecture is how do we do that and how do we propagate uncertainties through the various calculations. So consider a function. So let's begin with a linear function and then we will extend it to the nonlinear ones. A general case of a linear function of multiple variables, it will be f of x1, x2, have some constant term, let's call it 0, then a1 x1 plus a2 x2, and so that is, if this is function of multiple variables and it is linear with respect to all of its variables, this is how it will look. And then, as you know, variance is an additive parameter. We proved it in the previous lecture. So if we ask ourselves, what is the variance of f if we treat it as a random parameter that we got out of the experiment? Well, it is linear, and so it will be the variance of this plus the variance of that plus the variance of that. Variance of a0 plus variance of a1 plus variance of a2 plus so on. However, these coefficients, we shall assume that we know exactly. So the function, logarithm, sine, cosine, and so on, is known exactly. And so all of these coefficients, a0, a1, a2, and so on, are exact constants. And so the variance of a0 is therefore 0, so that disappears. And in here, the variance of a1 x1 is a product of the variance of, well, of just the exactly known coefficient and some uncertain variable here. What I will remind you, again from the previous lecture, is that variance was a quadratic function of what goes underneath. So variance of, for example, a1 x1 was defined in the previous lecture as the average value of the square of this, a1 squared x1 squared minus a1 x1 average squared. If we look at this constant, well, it's not a random variable, it's statistically independent, therefore, from a1, so we can take it out of the bracket. What will be there is a1 squared, then x squared, x1 squared average, minus x1 squared. And this is just the variance of x1. So a1 squared, variance x1. And so because variance is a quadratic function, the constant coefficients are taken out with a square. So in the result in here we will have a1 squared variance of x1 plus a2 squared variance of x2 and so on. Okay, so this is our variance of f. What we will also now note is that these coefficients, a1, a2, and so on, are actually partial derivatives of f with respect to the corresponding variable. So a1 is df by dx1, a2 is df by dx2, so ak is df by dxk in general. So why don't we rewrite this expression here in terms of those partial derivatives? So what we will get is variance of f, and I will now use the sum over all the variables that it has, sum over k, df by dk squared squared times the variance of xk. And for a linear function, this relationship is exact, because as we have seen, the errors just propagate straight, and the relationship for the variance of the sum and for the coefficients being taken out of the variances, we didn't make any approximations in here yet, so long as the function remains linear. And then, if you remember the definition from the previous lecture, sigma, the standard deviation, the parameter that you are more used to, was the square root of the variance of f. And And if we use it there, we will get the expression that the first years haven't seen yet, but the second years, I strongly suspect, have, because you did have to do error propagation at least at a simple level. Then our final result for the linear function is sigma f, the standard deviation of the function, is the square root of the sum over k dx by dx k squared sigma x k squared. So this is very important, and we will be using this a lot, and you will be using this a lot in all of your lab practicals. So what we have here is the exact formula for linear functions. But as I've already pointed out, in most cases, functions we are dealing with in chemistry are well behaved, and they therefore have derivatives, they therefore have tangent lines. And you can see in these cases that I've drawn on the board, using the tangent line instead of the function actually gets you a pretty reasonable estimate of your standard deviation. Now, the important point here is this is only a reasonable estimate if this error is small relative to the function. If we start having an error like this, which will then propagate to another colossal error in the output, then the linear approximation would no longer be reasonable. The same goes here. And therefore, we can extend this relation that we just derived to non-linear function, subject to the errors being small. So, for small, and we will not quantify these quantitative estimates do exist, but we don't have the time for them. For small standard deviations, you can estimate the standard deviation of any well-behaved function using the same formula. So sigma f is now approximately equal, and we should never forget that it is approximately equal to the sum over k df by x k squared sigma x squared. Alright, so that is more or less all we had to do by way of boring mathematics. So let us now try and derive a few error propagation expressions from this formula. It looks formidable, but it's actually quite easy to use because these partial derivatives are usually quite simple. So let's start with the standard thing, the sum. R1 f of x and y will be x plus y. Okay, so sigma f is going to be an enormous square root df by dx is equal to 1 squared times sigma of the corresponding variable, sigma x squared. That was the first variable. Second variable is y, df by dy is 1 squared sigma y squared. And so you get the standard error propagation rule for the sum that we have already seen in the previous lecture. You have undoubtedly seen in quite a few lab scripts. So sigma x squared plus sigma y squared. You are very occasionally told incorrectly to simply sum up these standard deviations. That is because this root is actually less than always, less than or equal to sigma x plus sigma y. And so if one uses this expression, one obtains what's called an upper bound on this. So you will obtain a worse estimate of the error. So your estimate will be pessimistic. But of course, this is a gross approximation. So you should always bear in mind that if you're doing that, then you've probably overestimated the error that you really do have. And so use the accurate expressions instead. Let's take a look at something more complicated. Is if our f of x is a product, so f of x, y is x, y, then sigma f will be approximately root df by dx is y squared times sigma x squared plus df by dy is x squared sigma y squared, and that is the standard deviation of the product. In principle, we can take x, y out of the root, so x, y with the modulus, and then you will have sigma x squared over x squared plus sigma y squared over y squared. And so that is actually the relative standard deviation relative to the amplitude. And again, oversimplified textbooks tell you that's x, y, sigma x over x, sigma y over y. And so the rules of thumb for these calculations is that for sums, standard deviations vary approximately add, and for the products, relative quantities vary approximately add. But I would suggest that by now you are grown up and you will not use the approximate expressions and use the accurate, well, in as much as the linear approximations here permit expressions for the error propagation. So let's go through another example. Let's say the ratio of the two variables. But this is all exactly the same. You just number your variables, and it could be x1, x2, x3, or it could be x, y, z, and so on. The expression is exactly the same. You carry forward the equations. So, practical example where we will have the ratio of the two. Let's say we're dealing with an ideal gas law, and we would like to know what the uncertainty is going to be in the pressure if we pack a cylinder with an uncertain quantity of the gas. We are not terribly certain about the volume of the cylinder, and we are not terribly certain about the temperature in the room either. So sounds like your typical undergraduate student doing the laboratory practical, so maybe we know where those variables are, but perhaps the error is significant, and I'd rather not that it exploded. So let us do the calculation and find out. So we have our pressure. It is, no, we need to calculate the pressure. It is unknown, and we've got the volume, which is exactly, would have been exactly a cubic meter if it wasn't for the standard deviation of it. 3 cubic meters. Then we've got the temperature, which is basically the room temperature. So 298 Kelvin, what passes for room temperature in Britain. Sigma T is 2. Standard deviation of 2. And then we've got our quantity is 0.3 moles with the uncertainty of 0.02 moles. Note how I am writing the quantities, and this is how all of you should be writing them. Even if the last decimal place is 0, you are still writing it to the last decimal place that you are certain of. So this last one carries some standard deviation, but it is still a significant place. If our standard deviation is 2 Kelvin, there's clearly no point to go into decimal places here, right? Never just write out the full output of your calculator, because somebody who reads you in the chemical literature will be misled into thinking that you are actually confident about all of those digits. So only quote to the decimal place on which you do have standard deviation. Okay, so we've got three parameters with three standard deviations. We want the pressure. As you know, P is nRT over V. And we do have one other variable in here, the gas constant, but of course the gas constant has been measured very precisely, and relative to the uncertainties that we have here, we can pretty much assume that that's the exact number. So we don't worry ourselves about the uncertainty in R. There are a lot of people who do have to do it in quantum mechanics. We're actually worried about things like the uncertainty in the G factor of the electron, which has been measured, if memory serves, to 12 decimal places. And it's still significantly consequential. That thing is uncertain, but not in this case. Okay, so using that expression over there, our sigma P is going to be approximately equal to, well, the variables are Vt and n, so that's our x1, that's our x2, that's our x3 in that notation over there. So the first thing we need to do is dP by dV. So dP by dV squared, sigma V squared, plus the next variable dP by dt squared, sigma T squared, plus dP by dN squared, sigma n squared. Well, I've been teaching you to take partial derivatives for many reasons, and this is one of those reasons. dP by dV minus nRT over V squared. So, nRT over V squared, sigma V squared, plus dP by dt and R over V squared, sigma T squared, plus dP by dN RT over V squared, sigma n squared, into which the parameters go for the reference point. So take the calculator, compute that, multiply by that, compute that, multiply by that, compute this, add it all together, do the calculation. The answer is 54 pascals. And the actual pressure that we get if we run that calculation for the reference point is 743 pascals. So standard deviation of approximately 50 pascals. 54 pascals. As you can see, the error is not terribly large, slightly less than 10% in this case, but there is equipment and there are situations where a 10% standard deviation is actually significant. So you can, in practice, with reasonable probability, have excursions up to 3 sigma in either direction. And so in this case, well, up to 20% fluctuation in the pressure might reasonably be expected. And so if you're an engineer building some cylinder, you'd better make sure that cylinder can handle those pressure excursions on either side. Okay, so that is your first example. And I've got a few more, but before we go into them, let's return to these examples here. Situations like this, where your error is magically compensated by the function you're dealing with, are exceedingly rare. In fact, in my practice, there were only 2 cases like this. Well, pH is the one case that I don't care about because I never actually go into the experimental labs. I haven't done any experiments in 15 years. But there are examples where what an experiment outputs is the 6th power of the distance between a couple of atoms, and then the 6th power root is something that also behaves in this way, and it smooths the error. But in most cases, what you unfortunately have is that the error is either preserved in roughly the same amount, or it is amplified. And the unfortunate situations where it is amplified will be the topic we have to consider next. And the situation is so common that it has a name. It's called catastrophic loss of accuracy. In Russian laboratory culture, well, because the word loss in Russian means an elk, people usually draw an enormous funny elk in this case, and there are multiple pictures about it and so on all across the labs. Okay, consider a situation like the following. You have your x, which you have measured, 2.219 plus or minus, so that's the standard deviation after the plus minus in this case, 0.090. A perfectly sensible value with a perfectly sensible error. Right? Not too much to worry about, nothing special here. This is what we do today. And then let's consider another variable y, which somebody else also measured, with also a pretty respectable error. Plus or minus 0.05. And then this arrives from one lab, that arrives from the other lab, and it is our job to calculate the sum of these things and the corresponding uncertainty. Okay, so x plus y will be, in this case, minus 0.007, so it's just the sum of that and that, plus or minus, if we take the usual error propagation law, so squared plus squared, that will be minus 0.007, plus or minus, once you do the calculation, 0.103. As you could probably have roughly seen, because the standard deviations roughly add when you add the variables together. So, something sensible with a sensible uncertainty plus something else sensible with a sensible uncertainty produced a number where the uncertainty is an order of magnitude greater than the number itself. Right? Such an estimate is completely useless for all practical purposes, because this number could be anywhere. Between 0.1 and minus 0.1, with about 50% probability, and between 0.2 and minus 0.2 with about 95% probability. So that's an example of catastrophic loss of accuracy. Let's consider something else. Let's say we're dealing with exactly this number, but our job is to calculate not the sum, but 1 over the sum. So what about 1 over x plus y? Well, we could have calculated the error estimates the conventional way, but let us take a look at the number we have just obtained. This is a small number, plus or minus 0.1. In this interval, from minus 0.1 to plus 0.1, we clearly have 0. Not only that, we've got 0 both on the left side and on the right side. So what happens when we approach 1 over 0 here from the right? Well, that's plus infinity. When we approach 1 over 0 from the left, that's minus infinity. So if we actually calculate all of this, then this will be 1 over minus 1 over 0.007. But actually, in this case, the linear approximation for the error breaks down, because we've got the possibility of having a 0 in there with a very high probability. Pretty much, the error estimate on this is plus minus infinity. So, whereas in that case, the number was useless, But perhaps if you are dealing with the quantity of matter or pressure or temperature, the error would have been painful and perhaps detrimental to the company's bottom line, but it would not have been catastrophic. In that, okay, you've underestimated or overestimated the quantity of the substance wildly. In this case, if this is pressure, God forbid, your reactor could go to plus infinity, and that means kaboom. So do be careful, because when you're manipulating uncertain quantities, particularly on a computer, which always does arithmetical calculations with finite accuracy, it's big, it's 64-bit, 16 decimal places and so on, but it is still a finite accuracy, and all of these numerical instabilities and error propagation and round-off errors and so on are, in my case, my daily companion. There are methods in mathematics that produce results accurately, and there are other methods in mathematics that just blow up exactly like this. Okay, so let's go through yet another example, and here we are returning to the concept of pH. So, imagine you have a friend, and we all have a friend like that, who is extraordinarily good at absolutely everything that they do, and they do the lab, and they proudly proclaim that I've just measured the pH to the decimal place. And, in their extremely accurately set experiment on an extremely accurate pH meter, the only one left in the lab, they have measured pH 2.1 plus or minus 0.1. Okay, you think, how do I show you? You stuck up a little. Well, you calculate the actual error that they have, right? You measure the logarithm, they've measured the logarithm, but you do know that the property that actually is consequential in chemistry is concentration. So, okay, they've measured the logarithm with this accuracy, but with what accuracy have they actually measured concentration? Okay, our pH, as we well know, is minus log base 10 concentration of the hydrogen ions, and therefore the concentration of the hydrogen ions is 10 to minus the pH. And if you look at the graphs that I have here, we are clearly in the situation where the errors are going to be amplified, because 10 to the power x is a pretty steep function. So why don't we run the error propagation through that? And we only have one variable in here, so it's going to be nice and easy. Our sigma h plus will be approximately the square root of the derivative of that with respect to the pH squared. So I will remind you that a to the power x prime is a to the power x log a. So that would be 10 to the minus pH log 10 squared. The minus we don't care about because that's the square, and then sigma pH. If we go through the calculator work in here, what we will discover is proton concentration is approximately 7.9 millimolar, and that standard deviation that we will compute after a lot of numerics is 1.8 millimolar. So the standard deviation in here is nearly 25%. And so no, they haven't actually measured anything accurately. The error is a quarter of the total quantity, and of course standard deviation is not a prescription for the error. The error can be greater. We don't go into the detailed probability and statistics, but the error could easily be twice the amount. So it would be a pretty reasonable statement to say that even though the pH has been measured quite accurately, the concentration of the hydrogen hasn't actually been measured accurately at all. And so you can stick it to your friend. Okay, so let's say that you then went and used a potentiometric titration machine and decided to measure the concentration of the H plus directly to whatever accuracy you can, and then use the reverse relation, which actually compensate errors, to get the pH. So let's find some space on the board. Let's say the machine gave us the following answer. H plus was, what do I have it here, 7.92 millimoles with the sigma of 0.03 millimoles. So reasonable quantity measurement devices can typically get you 4 decimal places of accuracy, but you've seen the teaching labs, we can get to 3 decimal places of accuracy in practice. Let's calculate the log of that, and let us calculate the standard deviations that that log might have. Okay, pH is minus log base 10 concentration of the hydrogen. Therefore, sigma pH is approximately equal to the root and the derivative of the log to an arbitrary base is 1 over the quantity times the natural log of the base. So 1 over H plus times 10 all of that squared times sigma H plus squared. So if we calculate that pH, we will get 2.1013, and if we calculate that, we will get standard deviation of 0.0016. So you are at least 2 orders of magnitude in the uncertainty better, measuring pH by measuring the concentration and then taking the logarithm of it. The morale of this story is that it rather depends, when you are dealing with uncertain quantities, which way around the mathematics you are going. There are functions that amplify errors, there are functions that compensate errors, and there are functions that roughly just pass them through, and you have to be aware of that. The general criterion is something that goes really steeply, like powers, exponentials, and so on, will amplify the errors as you are sending uncertain quantities through them, and things that taper off with their corresponding variables tend to reduce the errors in the answer relative to perhaps very large errors in the argument. So, okay, let's go through the summary of the lecture. Again, we have used the properties of the variances, that they are additive, to derive the exact error propagation law for linear functions. And then we observed that, well, for nonlinear functions, there doesn't seem to be any straightforward method to do that, and so we followed the rest of physics in just saying, okay, let's assume that the standard deviations are small, in which case the local linear term in the Taylor series is probably okay as an approximation, and why don't we use the same expression for the errors as we have derived for the linear function? Obviously, it would break if the error is not small. As soon as we have it, well, we know how to calculate partial derivatives of any function at all. We simply just do that. We multiply that by the square of the corresponding standard deviations. And here's our pretty good estimate of the standard deviations that we get out of those functions. And we instantly managed to derive the standard things that you will find in Monk and Monroe and so on. So any guide on how to process experimental data, this is all derived from there. The principal usage of that is practical safety. You'd rather make sure that something doesn't blow up. And here's an example of calculating pressure and the uncertainties in that pressure. However, there are dramatic examples, dramatic enough that they're called catastrophic loss of accuracy, which are surprisingly common, and the consequences can range from benign if you are calculating just the sum to absolutely disastrous if you are calculating something that can go into plus minus infinity as a result of the uncertainty in your calculations. And finally, you will all encounter pH, and this is probably the best example there is of a function that grossly amplifies errors in one direction and massively compensates errors in another direction. So do remember that when you are doing the corresponding arithmetic, that pH is in fact the law of the concentration. If you measure pH to this kind of accuracy, that probably means no accuracy at all on the actual concentration of the H plus. That's all I have to say for today. Any questions?